As you have heard, my name is Peter Gorham. I'm a professor here at the University of Hawaii, and my primary discipline is this, what Phyllis said, is called particle astrophysics. This catchy term comes from the idea that cosmic sources, stars and galaxies and all that stuff, produce not only light waves, which we can focus with a telescope, but they also make subatomic particles. This whole crazy zoo of things that physicists have gotten interested in the last few decades, and the things that make up anything that has weight, matter, all of that kind of stuff. My focus has been particularly in one such class of particles called neutrinos, which are by far the smallest and the lightest of anything that we have encountered. Before the discovery of the neutrino, we knew about electrons, we knew about quarks, which make up protons and neutrons, but we never really understood, one thing we didn't understand very well was why the electron was only about 1/2000th the mass of the protons and the neutrons. With neutrinos, the problem is much, much worse, because they weigh less than 1/1,000,000th of the mass of an electron. It's really kind of an absurdly small amount of weight at all. We have absolutely no idea why. It's even worse than that, because as to their size, neutrinos, we physicists measure the size of anything, any subatomic particle, by looking at how often they collide with other things, such as atoms, whose size we know very well. By this kind of measure, neutrinos that come, say, from reactions in the sun, one of the most common kind of neutrino around, are as much smaller than a proton as a proton is smaller than the entire Earth. So to say that again, if you somehow magnified a single proton, the nucleus of an atom, to be the size of the entire Earth, kind of a size we can all sort of barely comprehend, then a neutrino growing at the same rate would now be about the size of a proton. So if we thought their low mass was strange, then their relative sizes are far, far beyond strange. They're bordering on something unimaginable. The main effect of this very small size is that they just tend not to hit or bump into anything in the universe as we know it. We experience the universe according to the things that we bump into or bump into us. If you don't believe that, tonight, when the movie starts, light rays are going to collide with your eye, and sound waves will drive pressure into your ear, and you will experience Werner Herzog, at least some form of him. The vast majority of neutrinos in our universe, currently, they just pass right through everything that we know of without any contact at all. To a neutrino, your body, this auditorium, this building, all looks like empty space. Or very, very close to it. So, to me, what this means is that neutrinos, in some quantitative sense, are barely connected to our universe at all, except on a very, very wide scale by their collective gravity, which does have an effect that we can measure. This is why, if someone offers you the opportunity for some discount neutrino therapy or neutrino brainwave stimulation, I've been offered such things before, you should ask them to only be charged for the number of neutrinos that you actually use up, which will be 0. And I'm not really saying this because I'm not trying to talk you out of such therapy. It might help you, for all I know. But I am trying to get you a good deal. So to make a long story a little bit shorter, what got me interested in neutrinos was that they were provably real, but in some sense the most unreal, nearly unobservable, yet fascinating particle in any list that you could find. Many physicists since then have thought up even stranger particles than neutrinos, but none of these have been found yet. Neutrinos were discovered in the 50s, and we have been getting stumped by their properties ever since that time. But I have to say that for most of my career, I had no interest in going to Antarctica. Low temperature physics was not in my resume. What really took me, and this was unwillingly at first, to Antarctica was the same thing that fascinates us all about the place. As they say in real estate, location, location, location. In this case, the location is underneath 90% of the world's ice. 90% of that ice, most of it in enormous glaciers that are so big, we can't really even call them glaciers anymore. We call them ice sheets. But they are dynamic and they are moving. Much of this ice is at temperatures of minus 40 degrees Fahrenheit or colder. At those temperatures, as hard as granite. Much of it is several miles deep or more, as deep as the ocean. And below all of that is a continent of land we have never seen. And we should probably hope never to see, because if we could see it, life as we know it would have already come to an end. I'll get back to that. Now, in fact, we have seen this continent, but only with eyes that are made from radio antennas. This is due to the fact that this very, very cold Antarctic ice is utterly clear and transparent to radio waves, much the same way that glass is transparent to visible light. In fact, the ice is so pure that it is about 1,000 times more clear than glass in relative terms. By far the clearest material of anything that we can find on Earth. It allows us to see through it. If we had radio eyes, we can see through it for miles and miles. This has enabled scientists with radar to map the Antarctic subcontinent in great detail, because they're really looking through miles of what appears to be utterly clear radio glass. This is the property of ice that brought me to Antarctica. Because if you're interested in neutrinos, you got to get them to hit something, once in a while at least. And if they do occasionally collide with our universe, they're most likely to do it in the largest thing you could find around. But if they collide with an atom in the middle of a piece of granite, let's say, you're not going to be able to see it because you can't see through granite. So that neutrino is pretty hard to experience. If they do collide, for example, in the middle of a piece of Antarctic ice, and they produce a little bit of energy in that collision, in my case, in the form of a sharp burst of radio waves, which they do. If that is produced then, and that object that you're looking at, Antarctic ice, happens to be very, very clear, and you can see deep inside it, then you can detect that neutrino. So you get the picture here. Watch a whole bunch of ice with radio antennas, and if you see just the right kind of radio burst, you can pin it to a neutrino. And if you can see for miles and miles into this ice, and you get high enough up above the ice, say in a stratospheric balloon, then it turns out you can monitor 1 million cubic kilometers or cubic miles of ice at one time. And you have a super sensitive neutrino detector. So that is, in a nutshell, a project that Phyllis mentioned called ANITA. Well, there's a lot more to that, but that's what got me to Antarctica and has kept me coming back. Having been there, though, was not, for me, just a journey toward better science. It really opened my eyes to something deeper about Antarctica itself.